This PowerPoint is over experimental design. One of the important things when talking about experiments is knowing the difference between accuracy and precision. First of all, accuracy is getting the right measurement. So if you're measuring something with a meter stick, be able to get the right one every single time. Precision is where you get the same answer over and over again. So in designing an experiment, it is very, very important that you actually complete the same measurement over and over again in order to see consistency in your measurements. If something is inconsistent, then you need to throw that one out and try it again and make sure you're getting consistent. So just to give you a visual of where you can have the difference between accuracy and precision, if you potentially have a lot of measurements that are all in the same ballpark, that would be high precision, but if they're not close to the right answer, then that means they're going to be low accuracy. An example of this is something like if you're making measurements but you're making the same mistake over and over again. So let's say you're measuring something with a meter stick and you don't want to use the end of the meter stick, so you start at 10 centimeters and go over to 16. Well, if you call the measurement 16 centimeters, then you're going to be incorrect every single time, because from 10 to 16 is only 6. So that would be a great example of how you could have high precision but low accuracy, because you're not getting the right answer, but you're getting the same answer over and over again. In order to have high accuracy and high precision, you got to have both of those. You're not making any mistakes and you're getting the same answer over and over again. To have a high accuracy but low precision, this is an example of a student who just really isn't careful with their measurements. And oftentimes, if you're not careful with your measurements, then you can get a wide variety of measurements. If you're consistently trying to be very precise with your measurements, then they should all be about the same ballpark. And then if you have low accuracy and low precision, then obviously you're neither caring nor are you really trying to get consistent measurements. In designing an experiment, there's a lot of things you have to take into mind. First of all, to call it a controlled experiment, this term controlled means that you're only changing one thing that we call the independent variable. And that one thing that's changing is affecting something else that we call the dependent variable. So for example, let's say that you want to see if the amount of water given to a plant will change how high it grows. So in this experiment, you can see that the amount of water is what we're changing. That's our independent variable. And then the height of the plant, that's going to be our dependent variable. Included in that is you have to have everything else to be constant. So while you're trying to figure out how water affects the height of a plant, you wouldn't put one plant in the dark and the other plant in light, because that would be another variable that you would be changing. So everything else would be held constant when you have your independent and dependent variable. Next, you're going to come up with your procedures on how you're going to carry out the experiment and get your measurements. So first of all, you want to make sure your procedures are written in a list and that the measurements are going to be able to be repeatable. So if you have something that you're going to measure, you got to be able to repeat the experiment over again to be able to get the same measurement. You got to be able to do at least 3 trials of each one. So if you're measuring the height of something, you got to do it, measure the height several times to make sure you're getting the same results each time and it's consistent. If you get a height that's not consistent with it, then you throw that one out and try it again, redo a trial. So we're going to talk about how we build a timing device. So we're going to design an experiment for a pendulum. A pendulum is essentially a bob that's at the end of a string and it vibrates back and forth, kind of goes back and forth. And we have an experimental design worksheet that goes along with this. Some possible variables that could change the amount of time it takes for the pendulum to go back and forth. One is the length of the string. Another is the mass of the bob. This thing down here at the bottom is called a bob. And then the amplitude is how much the pendulum is pulled back from this position right here. So those are all possibilities of what could affect how long it takes to complete one cycle. And to give you that definition, that term for that definition is a period. The amount of time for one cycle is the period of oscillation. So we're going to make these 3 things our independent variables, so we're going to do each one separately. So if we change the length of the string, we're going to keep the mass the same and the amplitude the same, but changing the length and see how that affects period. And then we're going to change the mass, but keep the length the same and the amplitude the same and see how that affects the period, and the same thing with the amplitude. So after passing out the worksheet, it's very important that we keep these 3 things in mind when we come up with our procedures for this experiment. So in graphing the data, we're gonna make three graphs. One where each of our independent variables. So let's say, for example, it's length. That's going to go on the x-axis. Independent variable always goes on the x-axis. And the one thing we're looking at what it changes is the period, the amount of time it takes to complete one cycle. So length is going to be on our x-axis. The y-axis is going to be period. And a title that you can give this is going to be the y-axis versus the x-axis. So that's going to be the period versus the length, and that's a good title for this type of graph. If you change the amplitude, if that's your independent variable and looking at period, then it'd be period versus amplitude. Same thing with mass. It'd be period versus mass when you change that. So you're doing all three of those graphs. Now the next experiment we're going to do is a ball bounce. In doing this, we're going to basically bounce a ball and let it jump or bounce back up to whatever height it comes to. So we're studying if we drop the ball from a certain height, how high will it come back up? So we're doing varying heights. So heights from which we're dropped, that's going to be our independent variable, and then dependent variable is going to be the bounce height that it comes back up to. So the graph title is going to be y-axis versus x-axis, so that's bounce height versus the drop height. Now the relationship we're going to see in this experiment is it's going to be a linear relationship, which is going to follow this format. The x-axis again is going to be the drop height that's going to be put in, the y-axis is going to be the bounce height, and then the slope is going to tell us the relationship between the drop height and the bounce height. This will be able to help us make predictions. So if I tell you what height I want the ball to bounce to, then you could plug in that height you want it to bounce to, and then figure out what the drop height is going to be in the process.
So here we have an example of the bounce height versus drop height graph. So we have some data that we put in here. We got some data points from a previous student who had this, and then we do a line of best fit in order to see how the trend is matching in this. So with that being said, let's figure out some information about this. First off, let's calculate the slope. So in order to figure out the slope, we first have to take 2 points. So we're going to identify this point right here, which conveniently crosses at one of these lines here, and that crosses at 70-40. Then we'll go ahead and do another one that's at 140-80. All right, so with those 2 points, what we're going to do is we're going to do a rise of a run, and rise of a run, that means that we're going to take the 80 here minus 40, that's your rise, and then the run is 140 over 70. And then doing that, we plug that into our calculator where we get 40 over 70. We get that our slope is going to be 0.57. And now what that means is that 0.57 rise of a bounce height for every 1 centimeter of drop height. All right, so let's talk about the slopes meeting. As we just said, with the 0.57, that's going to be the rise of a run where the bounce height increases by 0.57 centimeters for every 1 centimeter of drop height. Now, if you look at this, it's basically just a reinterpretation of what we call the slope, and that's the rise of a run. So the rise, we look at the number is 0.57, so that's going to be 0.57 for the rise, which we see as centimeters of bounce height. And then for every, that's that divide, that over, and then we have 1 centimeter, that our run, the 1 centimeter of drop height. So whenever we say rise versus run, or rise over run, then we could basically reinterpret that, the rise being whatever's changing on the y-axis, so we got 0.57 and that y-axis there, and then for every 1 on the x-axis. And we could take any graph that we have and interpret it just like that, just by just plugging in what the y-axis is and what the x-axis here, and then the slope for there. All right, so our equation is going to be that basic format of y equals mx plus b. So let's plug in the numbers that we know. First of all, we already figured out what the slope is, so let's plug that in, 0.57x, and then plus our b. And you can see right here what the b value is. If we plug in our b value, which is 0, then we put that in there, and that's going to be our basic equation for this graph. It's going to be y equals 0.57 times x plus 0. Now with that, we can actually start making predictions. So let's predict how high the ball will bounce if it's dropped from 111 centimeters. With our equation, the 211 centimeters is going to be our drop height. That's what it's dropped from. So that's going to be plugged in, since that's our drop height, that's our x-axis, so it's going to be plugged into our x value. And so since that's our x value, then we need to figure out what the bounce height is going to be. That's the y-axis, so therefore we go ahead and plug in the y value is what we're trying to solve for. So then we plug in that 211 into the x-axis into the x value, we get 0.57 times 211 plus 0. And then we solve for y, we get 120.27. Now, if you know the bounce height lab, we can't really get to the nearest hundredth of a centimeter. So really what's realistic is 120 centimeters, since that's about as accurate as we're going to be able to measure. The precision is only going to be able to get to the nearest centimeter. Let's look at another example where we interpret what the slope is going to mean. So let's suppose we got a tectonic plate that's getting pushed above another, creating a mountain. The graph to the left shows the relationship of the height of the mountains with time. So interpret what the slope means. And you see here that the slope is going to be 2.3. We have a y-axis that's going to be height in centimeters, and the x-axis is going to be time in years. So we know that slope is going to be rise over run. So we're going to reinterpret this where the rise, that's going to be the y-axis, over, so for every one of the run, which is going to be time in years. So the rise, again, is going to be 2.3, and we're looking at centimeters of height. So the height is going to increase by 2.3 centimeters, and then over, that means for every run, which is going to be a year, for every year of time. So we've effectively taken the rise over run and reinterpreted each part, the rise being the slope of 2.3 for centimeters of height, and then over for every, and then run is going to be for every 1 year of time. And that's how you interpret a slope, is basically with the rise over run, reinterpreting that specifically to that graph.